Welcome to the Ontario High School podcast regarding Hess's Law. And if you're watching this podcast, you're likely either in a Chemistry 2 class or an AP Chemistry class. But this is part one of four. There are just a number of concepts with Hess's Law that require some time to extend. So the first one will deal with calculating enthalpies of reaction using an enthalpies of formation table. So, welcome. The change in enthalpy for a reaction is a state function. So if a chemical reaction is carried out in a series of steps, the delta H, or the change in enthalpy for the overall reaction, or net, is equal to the sum of the enthalpy changes for the individual reaction in each step. This is just a basic statement of Hess's law. Let's look at the reaction. In this case, it's the combustion of ethane burned in the presence of oxygen, forming carbon dioxide and water. We're going to calculate the enthalpy of reaction for this. This can also be described as an enthalpy of combustion, but the equation describes it. We're going to use the enthalpy of formations, the delta H, F, and that little zero superscript has to do with the standard conditions under which the enthalpy is calculated for these, but these are found in the back of your textbook in an appendix, and all major high school and college textbooks will have these tables. First, we're going to write the equations that describe the formation of 1 mole of each of the compounds from the constituent elements in their standard states. So for ethane, there would be 2 moles of carbon, which is a solid, and 3 moles of hydrogen gas combining to form 1 mole of C2H6. For carbon dioxide, 1 mole of solid carbon plus 1 mole of O2 to form carbon dioxide gas. And then for water, there is 1 mole of H2 plus 1/2 mole of O2 gas, forming 1 mole of liquid water. Two things with this are very important. When we deal with enthalpy changes, it is perfectly legal for us to use fractional coefficients, especially with an enthalpy of formation, because we're always looking at the value for the formation of 1 mole of the compound. Also, in the case of water, you need to watch very closely to see what the phase is, because the enthalpy of formation for liquid water is different than that for gaseous water or water vapor. Once we've written the equations for the formation of 1 mole of each of the compounds from their constituent elements in their standard states, we want to look up the delta H of formation for each of the compounds in the reaction and place them in a reaction table as shown on this slide below here. So you can see that for each of the 3 reactions, delta HF is written, and the signs are very important. And one of the things you'll notice is that we don't reference the 7O2 from this reaction with a place in this table, and the reason for that is the enthalpy of formation of any free element is 0, so we don't have to show it here. When we go to finish this problem later, you'll see how we deal with the O2. We're next going to multiply each of the reactions by the coefficient from the balanced chemical equation. So because there are 2 C2H6s, we need to get 2 C2H6s in our reactions below. So we multiply that by 2. For the carbon dioxide reaction, we multiply by a coefficient of 4. And for the water, we multiply by a coefficient of 6. So here we see the effect of multiplying by the coefficients from the balanced equation. We get 4 carbon plus 6H2 yields 2 C2H6. 4 carbon plus 4 O2 yields 4 CO2. And 6H2 plus 3O2 yields 6 H2O. These enthalpies have stoichiometric qualities to them. What's meant by that is if you multiply the reactions by a coefficient, you also have to multiply the delta H, or the enthalpy of formation, by that same coefficient. So because we multiplied the reaction for the formation of ethane C2H6 by 2, we have to multiply its enthalpy of formation, negative 84.68 kilojoules per mole, by 2. We do the same thing for the carbon dioxide and for the water. So you can see that reflected here. And now we look at the end result of multiplying by those coefficients. So here they are. Take a look at the table, and you can see these final values. They must be multiplied by the same coefficients as used for the individual reaction. Next, we want to examine the reaction equations in each of the steps. The compound form should be on the same side of the reaction equation as it is in the reaction we're interested in, which is written above. An equation can be flipped to ensure this, and if the equation is flipped, the sign must be changed to the opposite sign. If you look in the reaction we're interested in, C2H6 is a reactant, but in our equations that show the formation of ethane from its constituent elements, it's a product. We have to flip that around so that the C2H6s are on the same side of the equation, and when we do that, we then need to change that negative enthalpy of formation to a positive number. Now, the carbon dioxide and water are written fine as they are, because both carbon dioxide and water are on the product side as they are in the reaction that we're interested in. So as we look at this table now, you can see that reactions have been arranged so that the reactants are reactants, the products are products, and we're going to add them together with this caveat: we're going to cancel anything that is the same on both sides of the equation. So as you look at this, we can see that C2H6 is on the reactant side, as it is in the reaction we're interested in. There is hydrogen on the product side of the C2H6 reaction, and hydrogen on the reactant side of the formation of water reaction, and those 6 hydrogens will cancel. We also have 4 carbons on opposite sides of the reaction arrows, and so we'll be able to cancel those 4 carbons as well. Notice how our oxygens, we have 4 oxygens in the reaction of formation of CO2 and 3 oxygens in the reaction of formation of water. Because they're on the same side of the equation, we need to add those together. So here we go. So we've canceled the 4 carbons on each side. We've canceled the 6 hydrogens on each side. When we add these together, we get our 2 C2H6 plus 7O2, adding the 2 oxygen values of 4 and 3 together from the reactant side. We get our 4 CO2 and our 6 H2O. When we finish adding this equation together, it should look exactly like the reaction equation that we're interested in finding from these series of steps. So it does, so we're in good shape. Once we've added the reactions together and ended up with the same reaction equation as the one that we're interested in, we need to add the enthalpy of formation values together, being very careful to pay attention to the signs. So we're going to add positive 169.36 kilojoules plus negative 1574 kilojoules plus negative 1714.8 kilojoules. When we do that, we get negative 3119 kilojoules as the heat of combustion or heat of reaction for the combustion of ethane, C2H6. We got negative 3,119 kilojoules for the reaction or combustion heat of reaction for 2 moles of C2H6, but it's usually desirable to report the change in enthalpy of reaction in kilojoules per mole of the reactant. Since the change in enthalpy for 2 moles of C2H6 is negative 3,119 kilojoules, all we have to do is just divide that number by the number of moles represented in the balanced equation to put the value into kilojoules per mole of C2H6. When we do this, negative 3,119 kilojoules divided by 2 moles of C2H6 will give us negative 1,560 kilojoules per mole of C2H6 combusted. This is the end of Part 1A of Hess's Law. Part 1B of Hess's Law has a challenge problem for you to try. And so I strongly encourage you to go on and watch the Part 1B podcast. But this is the end. I want to leave you a quote by a wonderful author. It says this: "When we were children, we used to think that when we were grown up, we would no longer be vulnerable. But to grow up is to accept vulnerability. To be alive is to be vulnerable." I wish you well.